Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you. And this is the NPTEL MOOC course series, and the course is TQM2. We are in the fifth week. That means we have already completed half of the whole number of courses, and this is the 22nd lecture. And as you know, I am Raghunandan Sengupta from the from IME department, IIT Kanpur. So, to recap what we have done, if you remember that for in each of the classes, I tried to spend about 2 to 3 minutes trying to recap what we have covered in the last 2 or 3 lectures, and obviously if required I will go back to the initial lectures, give the bullet points. So, if you remember what our main concern is, there are factors, they can be factor A, factor B, factor C, factor D, whatever the numbers be. And we want to find out the interrelationship of the factors and the effect of the factors on trying to basically test some hypothesis. So, whatever the hypothesis, it can be, say for example, we think the mean values are equal for each factors, or it may be, say for example, one of the factors effect is dispersion or standard deviation is more than for the other, or say for example standard deviations for or the dispersions for all the factors are equal, and so on and so forth. Now, when you are considering the factors A, we basically try to find out the individual effects for A, for B, for C, for D, and then we try to find out the combined effects taking 2 at a time. So, if there are, say for example, capital N number of factors, it will be NC2, and if there are, say now if you consider the effect of the factors taking 3 at a time, it will be capital NC3, and so on and so forth. Now, when we consider the effect of the factors is basically to find out the total errors coming out from the effect of the factors taken 1 at a time, or 2 at a time, or 3 at a time. Once we do that, we try to find out what is the degrees of freedom. Once the degrees of freedom are found out, we try to find out what is the mean square. Once the mean square is found out, we find out whether the hypothesis is being rejected or accepted. Now, it also should be remembered that we intuitively consider the distribution per se to be normal. That is an assumption which may not be true, but we consider that in order to make our life simple. Then we also consider different type of other tests corresponding to the fact that you want the mean values to be 0 for the factors. Then we found out the so called test. So, all these are hypothesis tests considering the fact that the mean values of one of the factors, whether corresponding to the dispersions of the factors, which is tau suffix I, beta suffix j, gamma suffix k, where I is equal to 1 to small a, j is equal to 1 to small b, k is equal to 1 to small c, and so on and so forth. So, those can be equal, that not individually equal, that means tau is not equal to beta, but means tau i's are all equal for I is equal to 1 to a. Similarly, for beta, similarly for gamma, and we consider different types of hypotheses. Later on we saw that, say for example, if based on that, later on we saw that how the graphs could be drawn, how the factor planes could be drawn in order to find out whether there was linear relationship or non-linear relationship. Later on, yesterday for the last class, yesterday what I am using for the last class, which is this 22nd one, we did also consider that if the relationship was between a quantitative factor and a qualitative factor. So, let me come to the example of, say for example, the battery. So, what you have is say for example, the etching problem. So, when you consider the battery example, there were some temperatures which could be quantified, and there were materials which could not be quantified. So, they were basically a combination of qualitative and quantitative. it was all quantitative, then trying to basically do a so called regression modeling, considering the effects or the relationships are given by a simple regression modeling was easy, because all of the quantitative facts could be converted into a simple regression model and we can convert the problem accordingly and solve it accordingly. Now in case if there are quantitative, our main task is to find out that how we can basically do a mapping. This mapping I am not talking from the mathematical point of view, it is basically a more very simple from a layman's point of view, considering say for example there are 3 materials, so we will consider those 3 materials can be quantified in the scale of say for example -1, 0 or +1, or it can be -2, -1, 0, +1 and +2 depending on whatever number of factors they are. That means under each factor if the variation is very large, that means that there are many different type of factor levels, let me use the word levels. And then we saw that considering that we have been able to convert the qualitative one in the quantitative one, you can utilize again very simply in the models we have discussed in a simplistic sense, and try to find out what is the values of f naught. F naught means depending on what is the hypothesis, and then we can whether we can accept it or reject it. So let us continue discussing that further in the 22nd lecture. So if you consider the design expert output for the example 5.4, so which is the ANOVA model. So as you remember, and I have been always discussing, the first column would be all the factors. So it will be A, B, C if there are 3, then it will be A, B, A, C, B, C, then A, B, C, then the errors and the total one. The second column would basically be all the total sum of the squares corresponding to these factors. The third column is the degrees of freedom corresponding to these factors. Then you have the mean square errors corresponding to these factors, and the last value would basically be the f values and the p values. P values means the degrees of freedom level of confidence which you have, based on which you try to basically either accept or reject the null hypothesis. So in this you have the source of the models, and then you have A, B. Now here if you remember, I did mention that some of the problem formulations would be such that rather than finding out the linear relationship, it could be quadratic relationship also. So in this case what you are, sorry for that, in this relationship what you are doing, if you pay attention to the first column, this one, so they are factors, so called factors, which we will consider, which are basically now not AB. Apart from AB you have basically A square, you can have A square B, you can have AB square. Based on this you can find out what is the effect. So the sum of the squares, which is the effect of the errors for all these terms, are given. So basically for A square, the sum of the square is 76. For A square, I would not repeat the common one which we have been discussing, not AB, we will discuss A square B, the sum of the square is 7298. So I am leaving aside the decimal. Similarly you would also have some of the squares corresponding to AB square, and so on and so forth. Then you have the degrees of freedom. Once the degrees of freedom, you can find out the mean squares. Once the mean squares are value, you can find out the f values, and basically come to the conclusion whether you want to accept or reject it. Now corresponding, okay, here when you are putting the, say for example regression model, very simply you would basically have the r square and the adjacent r square. So adjacent r square would basically consider degrees of freedom, and you can find out the values and basically comment intelligently about the problem. So when you do the problem related to the temperature example, so you basically have temperature, then you have basically reading it along the first column. I will only concentrate on the important factors. It is A square, then you have A square B, and so on and so forth. So you have the coefficient estimate, the degrees of freedom, standard errors. I am just giving you the highlighted points. You have the coefficients, estimates, you have the degrees of freedom, you have the pre-adjusted r square, and based on that, once you find out the coded factors, the coded factors would be given by the values whether they are plus or minus, and then you basically solve the problem accordingly. When you try to find out the predicted life, so with respect to the temperature, So there would be different materials. Materials would basically corresponding to different factors which you have. So for the different materials, you will have the temperatures. If you remember, they were 15, 70 and 125. So they are plotted along the x axis. So this is 15, this is 70, this is 125, and based on that, if you have the life was basically in hours working. So you have the life, the different materials will give you different relationship, whether linear or non-linear. So in this case, I'll use a different color to highlight that. So this part is almost linear. So if you consider the other part, this one is non-linear, but it basically decreases as temperature increases, and the other part, let I try to use a different light color if possible. Oh, it's not coming. I'll use a hash. So this one basically is increasing till 70 degrees and then basically start decreasing from 70 to 125. So now we'll consider the concept of blocking in a factorial design problem. So you have discussed the factorial design in the context of a completely randomized experiment. So it was a random experiment, factors were decided, data set was considered considering a random experiment, and we did our analysis to either to prove or disprove the null hypothesis accordingly. Sometimes it may not be feasible, or it is not feasible or practical to completely randomize all the runs in a factorial model, because it may not be practical or it may not give you the exact answer. So for example, the presence of nuisance factors which would be there may require that the experiment be run in blocks. So say consider that during the you are doing an experiment, and for temperature 125 at some particular time the humidity is very high, which is not a factor to be considered, which means the external effects, white noises, nuisance parameter value, the effects are very high. So you want to basically do away with it. Or say for example, at a very low temperature the humidity is very low, or the pressure suddenly becomes very low, the environmental pressure based on which you are doing the experiment. So in that case, you would basically need to have a control on the experiment in order to do away with the external effects. So let us consider a factorial example with two factors A and B. So it would be AB, and the combination of AB would also come, A and B separately and then combination of AB coming. The linear statistical model would be giving like this, which is again I'll repeat because you have done it, I am sure you have understood it very well, but I'll repeat it in order to make it again very specific to the problem. The general concept remains the same. So what you have is basically the values are given by y. So if there are basically two factors A and B, the subscripts would be I for A, J for B, and K would be for the values from k is equal to 1 to small n. So that is why you see y suffix I, j, k. Then you will basically have the mu. Mu is basically the average of the average of the average, considering that you are trying to find out the average for all the n's, for all the a's, and for all the b's. So there will be three averages. Obviously you replace that mu value with mu hat and try to do your example accordingly, because mu hat is basically from the sample. Then you have basically tau y corresponding to the so called dispersion with respect to factor A. Then you have basically beta j corresponding to the dispersion of the movements from the average of the average of the average values corresponding to factor B. Then you have basically tau b suffix ij corresponding to the effects on both of them, and finally you have the error term which is epsilon ijk depending on whatever values of i's are there, j's are there, which in reading you are going to take. So as mentioned here, and as you can note down, I will just highlight it. I is equal to 1 to small a for factor A, j is equal to 1 to small b for factor B, and k is equal to 1 to small n for the number of observations, which is n. So here tau y, beta j and tau beta ij represent the effects of the factors A, B and AB intersection taken separately. So they are for tau is basically for A, beta is basically for B, and tau beta is basically for AB. Suppose that to run this experiment a particular raw material is required. So whatever the raw materials would be depending on the temperature variations. So this raw material is available in batches that are not large enough to allow all of these treatments. So how many number of treatments are there? There are A number for factor A, B number for factor B, and small n for the total number of samples. So the total number of so called set of observations we are going to take to do the study would be small a into small b into small n, as noted down here, which I am just highlighting. So consider the requirement is not large enough to allow all A, B, N treatment combinations to be done from the same batch. However, if a batch contains enough material for A, B observations, then an alternative design is to run each of these N replicates using a separate batch of raw materials in order to do the experiment. So basically consider the raw material variations may come out if you do not have the whole lot of raw materials to conduct the experiment, considering there are A into B into N number of observations. Consequently, the batches of raw material represent a randomization restriction or the block, and a single replicate of a complete factorial experiment is run within each block in order to basically understand what are the effects. So now, as I am basically considering the effects of the blocks, the model now intuitively changes in this way. Now listen to me carefully, you will understand. The effects are, we want to find out on y, I, j, k, which is there on the left hand side where I am pointing. Now on the right hand side we want to find out the factors or so called effects coming out of the factors. So that again remains mu, which is basically average of the average of the average. Tau suffix I remains, beta suffix j remains, tau beta suffix ij remains, the error term remains. Now we are also considering the effect for the kth block. So if we have basically divided it into blocks, so we will consider some delta based on which the effects of the blocks can be found out. In case, say for example, the overall raw materials for this example is changing and we are taking different blocks together for different raw materials. The raw material type remains same, but we are using raw materials at different intervals of time from different sources, so there may be variations in between. So which delta is the effect of the k block? So k, as you know, is basically from 1 to n, you have divided it accordingly. Of course, within the block, the order in which the treatment combinations are run are completely randomized, but outside. So if you take k blocks, for in each block they are randomized, but the different blocks have not been randomized, because if you remember, we are taking or consuming raw materials accordingly as they come. So they are not under our control. The model which is given here assumes that interaction between blocks and treatments are negligible. So if we consider the blocks and the treatments, their effects, or the so called, in a very simple terms, the correlations are zero. The analysis of variance is outlined in the following table. So what are these, and I basically go through them separated one by one. The table conceptually remains the same. The first column is basically you write down all the factors. So here if you note down, they would be for the blocks. They would be basic blocks means the k number of blocks you have considered. They would be effect coming from factor A, effect coming from factor B, effect coming from A, B combined. They would also be error, and combination of all these things would be the total error. The second column, I am only reading the column heading. Second column would be the sum of the squares. Third column obviously would be the degrees of freedom. Fourth column obviously very intuitively we can now say it would basically be the mean square error. Or the expected mean square values. Mean square would basically mean depending on whether you have all the observation for the whole population. If you do not have, you want to basically find out the expected value of that. And then obviously it will be the f statistic value, which will basically be the ratios of the mean square error which you have. Now if you pay attention, so I will only pay special attention to the values, individual cell values in this table corresponding to the second column, which is basically the total sum of the squares. Now if I consider the total sum of the squares, the blocks basically would mean that you have kept the blocks fixed, and for each block you have summed them up for all the factors A and all the factors of B, which means it will be y square, and the suffix you note down very carefully will be dot, because you are summing up for all the i's, second dot because you are summing up for all the j's, the k remains because the blocks are different. So, as mentioned here, it will be summation for all the k's y square dot dot k, and obviously if you want to find out the averages, it will be divided by a, and minus value would be obviously as it remains is the average of the average of the average squares, which is y square dot dot dot. So, dot 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 is for the suffix divided by a, b, n. Similarly, when you go to factor a and factor b, very intuitively it will be what? It will be summation y square, and if here is factor a, basically it will be I dot dot as mentioned here. I am just pointing my finger here, it will be y square suffix I dot dot, and outside it will be divided by b into n as it is, and the minus value remains as it is, which is y square dot 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 divided by a, b, n. Now, if you go to the factor b, it will be y square dot j dot as mentioned here divided by, because you are summing up for all the j's, it will be divided by a into n as mentioned, and the minus term would remains as it is, which is y squared suffix dot 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 divided by a, b, n. Now, when you go to the factors of a, b, so these values are, so these are basically SSA and SSB. So, SSA is here, and let me change the color, or let me put it like in this way. So, SSB. So, now if you want to find out for AB, so AB would basically be kept fixed for I and j, it will be y square suffix ij dot divide, and the whole term summed up for all the I and j's, and it will be divided by n, and minus term would always remains, and the minus, which is y square suffix dot 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 divided by a, b, n. But here also, as you are finding on the next level, the combination of a, b, it will be minus of SSA and minus of SSB, which you have already noted what they are. Then we find out the error term by the subtracting, and the total value remains as y square suffix basically ijk, because as you are finding it for all the values of ijk, minus term remains as it is, which is y square for all, so the dot remains for all the suffixes divided by a, b, n. Similarly, the degrees of freedom are found out. Now, again, even though I have not been discussing the degrees of freedom, I will still try to highlight it once again, but this is very intuitive and very simple. For the blocks, as there are n number of blocks, it will be n minus 1. For the factor a, as there are a number of factors, it will be a minus 1. For b, as there are b number of factors, it will be b minus 1. For AB, it would basically be a minus 1 into b minus 1, and the errors would basically be simply very simple like this. It is AB minus 1 into n minus 1, and you can basically do the calculations. And if you remember, degrees of freedom total or intuitively obviously remains a, b, n minus 1. Based on that, you find out the expected mean square. The expected mean square gives you the values based on which you will calculate f naught, and this f naught values are calculated where I am just highlighting. So, once you find out, you can either basically reject or accept the null hypothesis. The ANOVA estimate of the variance component of the blocks, which is basically corresponding to sigma square suffix delta, for the fact that delta is basically the so called dispersion we are taking for the blocks. It will be the mean square of the blocks minus mean square of the errors divided by a into b, because you have the sum up for all the factors number a and all the factor number b. The randomization was restricted to within a batch of raw materials. In practice, a variety of phenomena may cause randomization restrictions as time and operations, or raw materials quality being different from different batches. So, say for example, I get two different batches, one from vendor A and one from vendor B, and we want to maintain the quality. So, if it was only for vendor A, then those concept of randomization would have been taken place, but if they are not, then these concepts can be utilized in order to find out what is the effect. For example, if you could not run the entire factorial experiment in one day, then the experimenter could run a complete replicator on day 1, a second replicator on day 2, and so on and so forth. So, consequently, each day would be a block. Say for example, time is limited and he has to do the experiment, 8-hour shift is there. In the 8-hour shift, say for example, he does it for 3 number of blocks, and the rest remaining 2 he will do in the next day, which is day 2. And then they can be, the formulas as I considered can be, or we have discussed in the last few minutes, could be considered in order to basically proceed with the example to either accept or reject the whatever f hypothesis, null hypothesis was. So let us consider an example. An engineer is studying methods for improving the ability to detect target on a radar scope. Two factors she considers to be important are the amount of background noise. So what are the amount of background noise which is there, or the ground clutter or the scope of the type of filter which is being placed on the screen. An experiment is designed using 3 levels, the ground clutter and 3 levels of ground clutter. So depending on the effects, and there basically there are 2 type of filters for the noise filters. So we consider these are the fixed type factors. The experiment is performed by randomly selected treatment combination using the ground clutters, and then introducing a single representation of the target on the scope. So obviously it will have an effect both from the ground clutters and the filter types. The intensity of this target is increased until the operator observes it. So you are trying to basically increase the intensity in order to observe it on the screen. And because the operator availability is convenient to select an operator and keep him or her at the scope until all the necessary runs and the readings have been done. Furthermore, operators differ in the skill and ability to detect. So say for example, I am able to detect at a certain level of intensity, someone else is basically able to detect at a higher or lower level of intensity. So obviously those have to be considered when you are trying to do this experiment. Consequently, it seems logical to use the operators as blocks. So if there are 3 operators, I will consider operator 1 as block 1, operator 2 as block 2, operator 3 as block 3. So the number of experiments which I am going to do, I am going to divide it accordingly. That is very simple. Once an operator is chosen, the order in which the 6 treatments combines are run at randomly and determined. So it can be operator 2 doing first, then operator 1, then operator 3, or it can be operator 3, operator 2, operator 1. So whatever consequence we have or the sequence we have. Based on that, the data is shown in the table, which is ground clutter, which is low, medium, high, and you have basically the operator levels divided into filters of type 1, type 2, type 3 and type 4. So with this I'll basically go into the details of the values. So under operator block 1 you have basically 90 to 114. For operator 2 it is basically for filter type it is basically 86 to 93. Similarly for 2, 3, 4 the values are given, and based on that you can just plug in the values, which we will do in the next class, and try to basically understand how the problem is solved. With this I will end this 22nd lecture and continue discussing this problem where the factors blocks are considered in more detail, so that it becomes very easy for us to understand later on. Thank you very much and have a nice day.